Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for the upcoming task. So this task is going to be an investigation, and that means that rather than ask you heaps of questions that have nothing to do with each other, most of the questions will be centered around one application. We're looking at applying our knowledge of the course to real-world situations. Now, the sections of the course and test are linear relations, just a little bit on that, and mostly quadratics. So let's first look at applying linear relations to real-world situations. First, we have to understand what linear relation is. So if we have an equation of the form y equals mx plus b, we say x and y, these are the two variables, they are linearly related. We say they're linearly related because if I were to graph this equation, it would look like a straight line. It would look like this, leaning to the right if the gradient is positive, and it would look like this, leaning to the left if the gradient is negative, because this number in front of x is the gradient, and this other number by itself is the y-intercept. So this would be the y-intercept. So let's look at applying this to a real-world situation. So a plumber charges a call-out fee plus an hourly rate. He charges $2.60 for 3 hours, $5.40 for 7 hours, and we are going to calculate his call-out fee. So you might be wondering, well, what does this have to do with linear relations? Well, let's start by defining our variables. So we're going to let x equal the number of hours for which I hire the plumber, and y equal the cost, how much I have to pay the plumber. So remember, we always let x be the independent variable, y be the dependent variable. Cost depends on the number of hours that you hire the plumber for, rather than the other way around. So remember, because y depends on x, y is the dependent variable. So if I were to find an equation linking x and y, it would be of this form: y equals mx plus b. That's because the gradient here is constant. So applying that to this situation, the gradient being constant means for each additional hour you hire the plumber, the amount you pay goes up by the same amount. So each time x increases by 1, number of hours increases by 1, y goes up by the same amount. Constant gradient means linear. It means I'll be able to write it in this form. So it may not look like it, but this is actually asking us to find the equation of a line between 2 points. So the first point is hire 3 hours and cost is $2.60, and if we hire for 7 hours, cost is $5.40. So I'm going to find the equation of the line passing through these 2 points. So to find the equation of a line, you first find the gradient. So remember, y's go on top when you're finding the gradient. So we'll just substitute in y2 means y-coordinate of the second point, y1 means y-coordinate of the first point. So I get 540 minus 260, and then x2 minus x1. So if I put that on my calculator, I get 280 over 4, or 70. The gradient here is 70. What that means is for each hour, each additional hour I hire the plumber, the cost goes up by $70. That means the hourly rate is $70. So now I want to find b. So what I do to find b, the y-intercept, is I take my equation y equals mx plus b, because the line can always be written in this form. Now I'm going to substitute. So I'm going to substitute m for 70, which is the number I just found. I'm going to substitute x and y for one of these points. So I'm just going to choose this first point here. It wouldn't have mattered if I chose the second one. So in that first point, the y value is 260, so I'm going to change it to 260, and then I'm going to change the x value to 3. So now I have 260 equals 210 plus b. This is really easy to solve. You just subtract 210 from both sides. You get b is 50. So the equation linking x and y here, the cost is equal to 70 times the number of hours plus 50. This is telling us about the hourly charge, 70 times the number of hours, and this last part is the call-out fee. This is the amount you had to pay for 0 hours before the plumber starts work. So the call-out fee was $50. All right, now let's look at applying quadratics to real-world situations. So a quadratic is an equation of the form y equals ax squared plus bx plus c. It now has an x squared term, so it's not linear anymore. And if we were to graph this, we're going to have a parabola. So all quadratics have a turning point. So that turning point can either be like this, or it can be like this. So in this case, the turning point here is a maximum. There is a highest y value, whereas over here, the turning point is a minimum. So how you determine whether or not it's a minimum or maximum is really easy. It's totally determined by this value here for a. So if a is positive, then the parabola is a smiley face and has a minimum turning point, and if a is negative, the parabola is a frowny face and the turning point's a maximum. So we can easily find the turning point of a parabola by using this formula x equals minus b over 2a. So b is the coefficient, the number in front of x, and a is the coefficient of x squared. So when you found the x coordinate, you sub into the original equation, and you do that to find the y value, because this is a turning point. It needs an x value and a y value. So why am I telling you this? Because when we're applying quadratics, there's sort of like two types of questions. You'll either be asked to find intercepts or the turning point, because a lot of the applications of quadratics, you probably realized, are about the maximum or minimum of something. In fact, usually we're looking at the maximum of something. We've done questions like maximum height of the ball, maximum area, maximum revenue. That's where quadratics come in. Of course, linear functions, as we saw before, they don't have a minimum or a maximum, whereas quadratics do, and that's why they're really good for modeling real-world situations. So that's for the turning point. As I said, sometimes you'll be asked to find intercepts. So a parabola can have 0, 1, or 2 x-intercepts. So if it has one x-intercept, it looks like this, where the intercept is the turning point. It can have 2 x-intercepts like this, or it can have no x-intercepts, where it might be something like this, doesn't hit the x-axis. So you can determine the number of intercepts really easily by looking at the discriminant. So this will, if it has one x-intercept, the discriminant 0. If it has 2 x-intercepts, discriminant greater than 0. And no x-intercepts means a negative discriminant. So of course, remember the discriminant is that bit under the square root in the quadratic formula, b squared minus 4ac. So finding the intercepts is very useful in application questions as well. If we're looking at the trajectory of a ball, we might be looking at where the ball hits the ground. That would be an intercept. If we're looking at like profit, the x-intercepts would be where you break even, where revenue equals expenses. You're not making any money, but you're not losing any money, etc. So most application questions will either be finding a turning point or finding an intercept. Let's now look at an actual example. So let's look at this example. The trajectory of a ball thrown in the air is given by the equation y equals minus 5x squared plus 10x. So here we're saying x is the number of seconds after the ball has been thrown, and y is the height in meters. We're going to calculate the maximum height reached by the ball. So because it says maximum, or even if it said minimum, we should straight away be thinking about calculating a turning point. Now we don't need to graph this for the turning point, but I'm just going to quickly show you what the graph would look like so we can get an idea. So because this number in front of x squared is negative, it's going to be a frowny face parabola. It's going to have a maximum turning point. We could easily calculate here that the discriminant is positive. There will be 2 x-intercepts. So it's going to start at 0 because there's no c term here. So the graph would just look like this. Okay, we don't need to look at it going under here. That's not important to us because we can't really have a negative height here. So think of like an outfielder in cricket. They throw the ball up in the air, and it reaches a maximum height. Eventually gravity takes over and it starts coming down. So that's what's going on here. So as I said on the previous slide, the turning point can be calculated using the formula x equals minus b over 2a. Whenever it says maximum or minimum, we're looking at calculating the turning point. So in this case, b, the number in front of x is 10, and a, the number in front of x squared, is minus 5. So if I put all this into the formula, I get x equals 1. Remember, x is the number of seconds. What that means is the ball reaches a maximum height after 1 second. The question asks us to find the maximum height by the ball. It actually is asking us to find the maximum y value. So we found the x value of this point, we need to find the y value. So to find the y value, we just substitute our x value into here. So y would be minus 5 times 1 squared plus 10 times 1 equals 5. 5 meters is the maximum height of the ball. So it turns out that when we have equations like this number here is acceleration due to gravity. It actually should be about minus 4.9, but I just used minus 5 here for simplicity of numbers. So this number here represents acceleration due to gravity. This is the velocity of the ball in meters per second. So this ball would have been thrown at 10 meters per second. So then there is a term missing. Sometimes quadratics have a third term. They're trinomials. This number here tells you the initial height of the ball, the height from which it was thrown. So because there's no number here, in this case, it was 0. But what would happen if we change these numbers? This one's always going to stay the same, acceleration due to gravity. But what about these two numbers? If we change them, would they change the maximum height reached by the ball? So this number here is b. B was in the x formula for the turning point. So if I change b, I'm going to change the x value of the turning point. If I change c, because c was not in the formula for the x coordinate of the turning point, that won't change. So if I change b, it will change the x value of the turning point. If I change c, it won't have an effect on the x value of the turning point. If I change b or c, both changing either of them will change the y value of the turning point. So let's just look at an example of that. So if I add something like 2 on the end, that means that the initial height of the ball was 2. So that just shifts the parabola up by 2. So instead of starting at 0, everything's like up by 2, and it'll take longer to hit the ground. So if I change it there, the turning point, the x coordinate of the turning point would still be 1. B is still minus 10, A is minus 5. But the y coordinate of the turning point, I would just add 2 on the end, and then that would mean that the maximum height becomes 7 instead of 5. So if I change this value of c, you can see that it's changed the y value but not the x value of the turning point. So if I were to change what b is, so let's say that instead of 10 meters per second, the ball travels at 20 meters per second. And let's say it's thrown from an initial height of 2. So now if I calculate the turning point, it will be minus b over 2a, which is actually 2. So now, by changing this velocity, this ball will reach a maximum height after 2 seconds. So what will happen is it starts here at 2, goes like that. After 2 seconds will be the maximum height. So to find this y value, once again, we substitute the x value into the equation there. So the y value would be minus 5 times 2 squared plus 20 times 2 plus 2. If you put that on your calculator, you get 22 meters. Okay, so that would be the maximum height of the ball if I've changed the velocity to 20 and the initial height to 2. So I'm now going to rub out all the working down below. Please pause and copy it down if you need. So now we've got the same equation, y equals minus 5x squared plus 10x plus 2, but we're being asked how long until the ball reaches the ground. So how long until it reaches the ground means what is the x value when y equals 0? Because y is the height in meters. So if it hits the ground, y is 0 meters above ground. So this is an example where we're trying to find an intercept. So again, what is happening here is the ball starting at 2 meters, initial height goes up, reaches its maximum, and it'll come down and eventually hit ground level. We want this value here. Now there will also be another value over here. We're not going to accept this value here because it would be negative time, which doesn't make any sense. So all we have to do to solve this question is take our equation and we're going to change y to 0 and then solve. So when we're solving something, the easiest way is probably to use the quadratic formula. So that's what we're going to do here. It's so much easier than completing the square. This one can't be factorized, so quadratic formula all the way. So first we calculate the discriminant is b squared minus 4 times a times c. So if you put that on your calculator, you get discriminant of 60. Because the discriminant is greater than 0, there will be 2 solutions, meaning there'll be 2 x-intercepts of the parabola. So because this is not a perfect square, both of them will be irrational. So let's now use the quadratic formula. So this is the quadratic formula. So in this equation, x will be minus b, so minus the number in front of x, plus or minus the square root of the discriminant, all divided by 2a. And of course, a in this case was minus 5. So there are 2 solutions here. Minus 10 plus root 60 over minus 10, or minus 10 minus root 60 over minus 10. So if you put these both on your calculator, one solution is about 2.18. The other solution was minus 0.18. And as I said, we're going to reject this solution because we can't have negative time. So it would take about 2.18 seconds for the ball to hit the ground. All right, let's now look at a harder question involving this ball in the air. So let's look at this question. Another ball is thrown in the air. Initial height 6 meters. It was 22 meters above ground after 2 seconds, 15 meters above ground after 3 seconds. And now we're asked to find the quadratic equation of the trajectory of the ball. So almost all the applications involve finding an intercept or finding a turning point. This is just one of those really hard questions where we've actually got to find the equation, a quadratic equation. So what we do here is define our variables. So just like in the last example, x is going to be the number of seconds after the ball is thrown. X is time, the independent variable, and y is going to be the height in meters above ground of the ball. So y is dependent on x. So what we have here are 3 points. So if the initial height was 6 meters, after 0 seconds, the height was 6. After 2 seconds, the height was 22. And after 3 seconds, the height was 15. So graphing these points probably wouldn't help, but I'm just going to do it to show you what's going on. So if we had our axis here, so it started an initial height of 6, and after 2 seconds, it's gone up to 22, and then 3 seconds, it's down here at 15. So the trajectory of the ball is going to be a parabola like this. We're just being asked to find the equation of a parabola given 3 points. So this is a tricky thing to do, but we know how to do this from class. So remember, the equation of any parabola is going to be y equals ax squared plus bx plus c. It's just a matter of finding the coefficients a, b, and c. So remember, c gives you the y-intercept. So because it's initially 6 meters, c is actually 6. So that's easy to find the first one. So we'll rub that out and write C for 6. Now to find A and B, I'm going to substitute these 2 points into this equation one by one and come up with some simultaneous equations. So if I substitute in the first point 222, I'm going to take my equation here, replace y with 22 and x with 2. So I get y equals a times 2 squared, so x squared is 4. So then bx, so b is what I'm trying to find, x is 2, so it's going to be 4a plus 2b plus 6. I can, of course, rearrange this to 16 equals 4a plus 2b. Now we're going to do the same for 315. So we're going to take our equation, change y to 15. So x squared is 3 squared, which is 9. Here, b is what I'm trying to find. X is 3, so bx is 3b plus the 6 for c. So that, of course, means 9 equals 9a plus 3b. So to find A and B, I use these two simultaneous equations. So I'm going to use the elimination method. I'm going to times the top by 3 and the bottom equation by 2. That will make the B's have the same coefficient. So the top equation becomes 12A plus 6B. I also need to multiply the 16 by 3, and then for the bottom one, I times 9a by 2 times 3b by 2 and times 9 by 2. So now I subtract, I get minus 6a equals 30, and I get a equals minus 5. So then you can substitute a minus 5 into either any of these equations, it doesn't matter, and you should get b is equal to 18. So that means that the required equation is y equals a x squared plus bx plus c. So they are hard questions when you're finding the equation. All right, now we're just going to look at another example in which we are applying quadratics to real-world situations. So let's do this question here. The perimeter of a rectangle is 36 centimeters. What is its maximum possible area? So maximum possible, straight away you should think of quadratic equations and turning point. So we need to come up with the quadratic equation, and first we need to come up with a variable. So we're going to let x be the length of this rectangle. To find its area, we need to know its length and its width. So I'm going to write the width in terms of x. I don't want to let y be the width because then I'd have 3 variables. I'm going to let y be the area. So if I put another variable here, I'm going to have 3 variables, and I don't know how to solve quadratic equations with 3 variables. Instead, what we're going to do is we're going to write the length in terms of x. So if the length is x, the width is going to be 18 minus x. That's because the length and the width add to half the perimeter, because double this plus double this equals 36. So, if the length was 12 centimeters, the width would be 18 minus 12, which is 6, because 12 plus 12 plus 6 plus 6 equals 36. So if y is the area, y is just the length times the width. So this is another area where quadratics are useful. When you're multiplying two things that rely on the same variable, in this case the length. So if I expand the brackets here, I just get 18x minus x squared. So that's y, the area. If I want to find the maximum value for y, you guessed it, turning point. So I'm going to let x equal minus b over 2 times a is minus 1 here, which is 9. So if the length is 9, the width will be 18 minus 9, which is also 9. So that will be the maximum area. When x is 9, the area will be 18x minus x squared, or 81. So 81 centimeters squared is the maximum possible area. Once again, maximum possible, all we really did was find the turning point. Here, it was just a bit of work to come up with the equation. All right, let's look at the third and final application of quadratics that we're going to go through. So another common application of quadratics is in economics when we're looking at revenue or profit. The reason quadratic equations help is just like in the previous example, we have a situation where we're multiplying two things that depend on the same variable, and I'll get to that. But first off, we're told this. Price depends on the quantity sold. I sell 10 shirts at $30, 6 shirts at $50, and we're going to find a linear equation linking x and y. So this is, again, finding the equation of the line going through 2 points. So I'm going to let x equal the quantity sold and y be the price, because it said here that price depends on the quantity sold. In actual fact, they depend on each other. So if you're selling a lot of something, the price will go up if a lot of people want it. And if not a lot of people are buying it, the price goes down. So they depend on each other. So to find the equation linking x and y, we've got the first point, so quantity and price, and the second point, quantity and price. So we're just going to do what we did before. We're going to find y equals mx plus b. Firstly, we find the gradient m, y2 minus y1 over x2 minus x1. So that is 20 over minus 4, which is minus 5. If we substitute in, we should find that b is equal to 80. So the equation linking x and y is y equals minus 5x plus 80. So what this essentially means is each time the price goes up by $5, you lose one customer. So if I increase the price from 30 to 35, I would expect to only sell 9 shirts. If I increased it to 40, I'd expect to sell 8 shirts. Each time you increase the price by $5, you sell one fewer item. So this is why we have a negative gradient here. So you're probably thinking, well, what does this have to do with quadratic equations? Well, let's say now I want to look at the revenue. So you know the revenue, the amount that you make, is just the price times the quantity, which I'll just call Q. So this is the price. Y is the price, X is the quantity. So the revenue, the amount of money I make, is quantity times price. That is a quadratic equation. If I expand it, I get minus 5x squared plus 80x. So that is the revenue I will make from selling these shirts. So what if I wanted to find the maximum revenue? So if I find the maximum revenue, all I'm doing is finding the turning point of this quadratic here. So the turning point is going to be x equals minus b over 2 times a. And if I put that into that formula, I get x equals 8. So the maximum revenue will occur if x is equal to 8. That means if I sell 8 of these. So if I sell 8 of these, then the revenue is just going to be if I substitute 8 into this formula. So if I put 8 into this formula here, minus 5 times 8 squared plus 80 times 8, I actually get $320. That's the maximum revenue I'll make. So note up here, if I sold 10 at $30, my revenue would be 10 times 30, I'd only make $300. And similarly, 6 at $50, I'd only make $300. But if I sell 8 at $40, I'll get $320 in revenue. But note, this doesn't say anything about profit, so we're going to look at profit on the next slide. So I just calculated I'd make the most revenue if I sold 8 shirts at $40. I'd get $320 from this quadratic equation here. But if the shirts cost $2 each to make, will this number give me the maximum profit? So the revenue I make, the amount of money I make, was given by this equation here, right? But if each shirt takes $2 to make, the profit I make is going to be the revenue, which is this, minus the expenses, minus $2 per shirt. So then the profit would be minus 5x squared plus 78x. So what we've done by saying that each shirt costs $2, we've changed the value of b. And earlier in this video, I told you that will change both the x and y value of the turning point. So the turning point, the maximum will now occur at minus b over 2 times a. So the maximum now will be 7.8. So that means I should sell on average 7.8 shirts. So it's impossible for me to make 7.8 shirts, but that could mean I average 7.8 shirts per week or per month or whatever. I just want you to be aware that the number of shirts that maximizes revenue is not necessarily the number of shirts that maximizes profit. And again, that's because I said before, if you change this value b, you change the x and y coordinate of the turning point. So if I substitute x equals 7.8 into this equation here, I get $304.20, which is the maximum profit, all right? So now we're going to see how many shirts I need to make in order to break even. So please pause and copy this down if you need. So if I want to find the number of shirts to break even, I want to find where profit equals 0. Break even means cost and revenue are equal. You're not losing any money, you're not making any money. So that's just one of those examples where I'm asked to find the intercept of this equation here. So if I have profit equals 0, I get 0 equals minus 5x squared plus 78x. So for this one, you could use the quadratic formula or you could factorize. If you factorize, you take out a common factor of x. And so either x equals 0, well, that's really not enlightening at all. We know we're not going to make any profit if we don't make any shirts. But we can find the other solution. If minus 5x plus 78 is equal to 0, you can add 5x to both sides and then divide by 5, you get 15.6 equals x. So if you make 15.6 shirts, or about 16 shirts, you break even. So what that means is we're going to look like this. At $0, I'm not making any profit. So what it's going to do, the parabola is going to look like this. So I found before that 7.8 is the sweet spot. That's where the profit is maximized. And over here at 15.6, that's when I stop making money. So if I make any more shirts than 16, if I make 16, 17, 18 shirts, I'll actually be losing money. So that's why this sort of modeling is very important in the real world. It isn't always a case that you just, the more you make, the more profit you have. And this gives you one example where that's not true. So interestingly, note the turning point is always halfway between the two x-intercepts. It's halfway between 0 and 15.6. That's not a coincidence. It happens with every parabola. All right, sorry that this video was long. Thanks so much for tuning in. Best of luck studying. You're a superstar, and I wish you all the best. This has been the luckiest maths teacher in the world. Have a great day.